In a simple harmonic motion, an object oscillates back and forth along an equilibrium position. A typical picture for displacement as a function of time look like the following. So here is the position axis, and here is the time axis. It's t. The beginning of time is here at the origin, and a typical diagram look like this for the simple harmonic motion. So now if we look at these kind of diagram, we see that it repeats itself after a certain time, such as this section of the motion is repeated afterwards at this location. So to describe such a motion, we call this one cycle. And the time taken to finish one cycle is called a period. The symbol for it is capital T. And here, if you read it from the time axis, that's the period T. And here is the 2 cycle. We get 2 capital T, okay, and so on. So that's called a period. Its unit is in seconds. SI unit is in seconds. Now, the inversion of this quantity, we defined it as frequency. The symbol is F, which is given by 1 over T. Now its unit is per second, which is hertz. Right, we have a special name for it. And the frequency here represents the number of complete cycles in one second that can be done by the object. Okay, so one example is, let's say the frequency is 20 hertz. That means that in 1 second, we're going to have 20 such complete cycles finished by the object. So you're going to see like 1 second here, and there are 20 complete cycles. Okay. And there's an associated frequency called angular frequency. The symbol for angular frequency is omega, a Greek letter, and it's defined as 2 pi times f. Right, 2 pi f is defined as angular frequency. And its unit, SI unit, is radian per second. So now let's look at the solution to a simple harmonic motion. We said previously that, let's say for displacement, it is given by A cosine omega t plus phi naught. That's a general solution to a simple harmonic motion. And frequency appears here, angular frequency appears here in the solution. And it can be very useful if we know this definition of the omega. So from here, we can easily calculate the regular frequency from omega over 2 pi. And you can also calculate the period by 2 pi over omega. Okay, so that's when you see a solution like this one, you can immediately calculate the frequency or the period of this simple harmonic motion.